Hey, welcome to The Explainer. So, have you ever wondered how we can teach a computer to make decisions? And I don't mean with lines and lines of complicated code, but with something as simple and intuitive as a flowchart. Let's dig in.
All right, so here's our game plan. We're going to start with the basics, making decisions from data. Then we'll get right into what a decision tree actually is. From there, we'll look at how these trees learn, which involves a really neat concept called entropy. After that, we'll tackle a major hiccup called the overfitting problem, and wrap up with a really clever solution, random forests. Okay, let's kick things off with decisions from data. The big question here is, how can we build a system to predict outcomes when all we have is a simple table of information? This is a super common problem, right?
So, let's imagine you're a hiring manager. You've got this data set of all your past candidates. You've been tracking things like their experience level, their favorite programming language, whether they use Twitter, if they have a PhD, and then you've got the most important piece of information. Did they end up interviewing well? Now, the real goal is to use all this history to predict how new candidates are going to do.
So, here's the core question, right? Given all this data, how can we automate the decision-making process? How can we get a machine to learn the patterns here so it can make a smart guess about a brand new candidate it's never seen before?
Well, that brings us right to our next topic. What is a decision tree? It's a surprisingly intuitive model, mainly because it mimics how humans actually make decisions. It's powerful because it's so easy to follow.
Okay, so what is it really? At its core, a decision tree is just a flowchart. It's a model that uses a tree-like structure of decisions. It starts at the top and just asks a series of simple if-then-else questions to sort through the data. Each answer sends you down a different path until you land on a final answer.
And there are some huge advantages to this approach. The biggest one? They're incredibly easy to understand and interpret. I mean, you can literally print one out and show it to someone who's not a data scientist, and they'll get it. Plus, they're super flexible. They can handle both numerical and categorical data, and they can even work with data that has some missing values, which is, a lifesaver.
All right, so this all sounds great in theory, but this brings up the most important question. How do these trees actually learn? How in the world does the tree know which questions to ask and in what order? It's got to have some kind of strategy, right?
Exactly. The algorithm needs to figure out what the best attribute is to split the data on at each step. It needs some kind of yardstick to measure which question will give it the most clarity, which question will get it closer to a confident answer. Basically, it's looking for the question that best separates the yeses from the nos.
And the answer lies in this concept called entropy. It's a measure of impurity or uncertainty in a set of data. Just think of it like this. High entropy means high disorder. Everything is mixed up and chaotic. Low entropy means high purity. Things are nicely sorted and predictable.
Here's a perfect example. Look at this group with 5 hire and 5 don't hire labels. It's a complete toss-up, right? Totally unpredictable. That's high entropy. Now compare that to the other group, 9 hires and just 1 don't hire. That's almost completely pure. It's predictable. That's low entropy.
So the goal is simple. The algorithm wants to ask questions that create the purest possible subgroups it can. It's always looking for the question that will cause the biggest drop in entropy. It's a greedy approach. At every step, it picks the single best question for that immediate split, the one that makes the resulting groups as clean and predictable as possible.
But there's a catch. This approach has a pretty big weakness, and that brings us to the overfitting problem. So what happens when a model learns the training data, too well? It sounds like a good thing, but it can actually be a huge issue.
And this quote really says it all. It is very easy and very bad to build decision trees that are overfitted to the training data. And this isn't some obscure theoretical problem. It's a really common and serious pitfall. It's a classic mistake to let your tree get way too complex.
So what exactly is overfitting? Well, it's when a model learns the noise and the very specific details of the training data so well that it actually performs poorly on new, unseen data. The classic analogy is perfect. It's like memorizing the answers for a test instead of actually learning the concepts. You'll ace the practice test, for sure, but you'll fail the real exam.
And you can really see the difference here. A model with good generalization is like this small, simple tree with clear paths. It captures the main patterns. But an overfit model, it looks like this large, complex tree. It's got so many branches that it basically isolates individual data points. It's created a special rule for every single example it saw, which makes it totally useless for the future. So, if one single, super detailed tree can be this flawed, what's the solution? Well, what if we use a whole forest? This brings us to a really elegant fix.
The solution is called a random forest. It's an ensemble model, which is a fancy way of saying it's a team. Instead of building one huge, complicated tree, it builds many simple decision trees and then combines their predictions. It's all about the wisdom of the crowd.
And the process is actually really straightforward. First, you create a bunch of smaller data sets by just taking random samples from your original data. Then, on each of those samples, you build a simple, slightly different decision tree. Now, when you need to classify a new point, you just let every single tree in your forest make a prediction. They all get a vote. And the final decision? It's just determined by a majority vote. The most popular answer wins.
And the result is pretty amazing. Random forests are fantastic at reducing overfitting, and because of that, they often lead to much better predictive accuracy than you could ever get from just a single decision tree. It's that strength in numbers idea. Any one tree might be a little bit wrong, but the errors of all the different trees tend to cancel each other out. And this leaves us with a really fascinating thought to chew on. What other problems could be solved, not by trying to build one single perfect model, but by assembling a whole team of simple ones? This wisdom of the crowd idea is so powerful, it really makes you wonder where else it could be applied.
So if you like this explainer, please share it with your network. And of course, subscribe for more deep dives into complex topics. We'd really appreciate it. Thanks for watching.